Today we're going to take a look at 11.2 day 2 and we're going to explore further some chord measurements. Now a chord, before we get going, and remember, is a line segment whose endpoints are on the circle. And arc, remember, is just an unbroken part of the circle. So a quick definition before we jump in. First of all, congruent arcs are two or more arcs that have the same measure. We're going to explore this little theorem here that has something to do with congruent arcs, congruent chords, and congruent central measures. Central angles. So down here in our little GeoGebra exploration, we have two central angles, the central angle DAB and central angle CAE. And you can see that as we move them and make them bigger, they can continue to stay congruent to each other. Well, we also remember that minor arcs, such as DB and EC, are going to have the same measure as their central angle. So DB is also going to be 97.4 degrees, and same with arc EC, 97.4 degrees. So what you're seeing here is that if I have two congruent central angles, that I'm going to have two congruent arcs as well. Well, there's another part of this that fits into play here, and the chord that is formed, we're going to just show those chords. The chord that is formed between the points of an arc, such as CE and DB, are also going to be congruent to each other when I have congruent central angles. So here you see that there's an arc length an arc length of 103.1 degrees and the chord length of DB, which is equal to 5. Same thing over here. I have a central angle of 131 degrees and a chord length of 5. So my theorem up above really just ties all three of these links together, all three of these congruent measures. So what the theorem says is congruent central angles have congruent chords. So here's my two congruent central angles. That means chords AB and CD are equal to each other. And if I have congruent chords, then I have congruent arcs. Therefore, AB is congruent to CD. And if I have congruent arcs, I know that my central angles must be congruent. So it's kind of like one big circular congruency thing. If one pair is congruent, then all the other pairs are congruent too. So let's take a look at our first example here. It says if HLG is congruent to JLK, what two statements can you make regarding the chords HG and JK? And how about arcs HG and arc JK? Well, here's my two central angles. HLG right here is congruent to JLK. So when I have two congruent central angles, I know that my chords HG, it's a line segment, have to be congruent to JK. And I also know that my arc HG must be congruent to my arc JK. So those are my two statements that I'm going to make. And I know that if they are equal to each other, I can set the two statements equal to each other and I can find my value of y. So 2y plus 5 is equal to y plus 13. Simply going to combine my like terms. I'm going to subtract y from both sides. That's going to leave me with just y on this side now. And I'm going to take my 5 and move it over by subtraction. So that's 13 minus 5, which is 8. So y is equal to 8. In our next example, we're given that TV is congruent to SW. So TV is a chord. It's congruent to SW. And I'm given expressions for these arcs, arc TV and arc SW. Well, I know that chords are congruent, therefore the arcs that go between TV and SW must also be congruent. So I'm simply going to set their expressions equal to each other, and I'm going to solve for the value of n. So I'm going to combine my like terms, move my 7n over by subtraction. That leaves me with 2n. And now I'm going to add my 11 over here, and that leaves me with 22. Divide 2 off of both sides, and my value of n is 11. In example 3, it says circle B and E are congruent. Remember, and when I have congruent circles, I know that their radii are congruent. It says, and so are arcs AC and DF. So here's arc AC, and here's arc DF. I want to find the measure of angle DEF. So DEF is the central angle, If I find the value of the arc DF, then I know the value or the measure of that central angle DEF. So I'm going to start by setting these two equal to each other and finding my value for y. So 12y plus 20 is equal to 10y plus 36. Subtract my 10y. That gives me 2y on this side plus 20 is equal to 36. Now I need to subtract my 20, and I'm going to end up with 2y is equal to 36 minus 20, which is 16. Divide off the 2, that gives me a value of y to be 8. And now I need to find the length of that arc, or sorry, I should say the degree of that arc. So I plug 8 back in for y. That's 10 times 8 plus 36. That's 80 plus 36, which is 116 degrees. And I say that that's also the measure of that central angle, DEF, is equal to 116 degrees. In the next part of Chapter 11.2, we're going to take a look at chords being bisected. And this theorem here, this truth about circles, says this. If a radius is perpendicular to a chord, then it bisects the chord and its arc. So if you take a look at our picture here, you see that the radius CD, it's coming through and it's perpendicular to the chord EF. Because CD is perpendicular to the chord EF, I know that EF is being bisected. I also know that the arc EF is being bisected as well. Remember, if something's being bisected, it's being cut up into two congruent parts. The next one says the perpendicular bisector of the chord is the diameter. So any chord and the diameter will be perpendicular to each other. So as long as the diameter is bisecting it, bisecting that chord. So here is our diameter, JK, and it's coming through the center of the circle, point A, and it is perpendicular and bisecting GH, that chord. So my conclusion here is that if JK is the diameter and JK is perpendicular to it, then JK is the perpendicular bisector. So let's take a look at an example of how we're going to use this to problem solve. It says if RS is equal to 8, if I'm taking a look over here at my circle R, and RS is equal to 8, and then it says SM is equal to 9, find the length of chord NP. So here's our chord NP. I need to find the length of it. So here's my radius. Remember, any point or any line segment that goes from the center to a point on the circle is called the radius. So I know the radius of my circle here is 8 plus 9, which is 17. So I can draw another radius here to help me out. I'm going to draw the radius Rn. So any radius is also going to have the same value. Therefore, Rn is going to be equal to 17. In a sense, what I've just done is I've created a right triangle. I know that this is perpendicular because Rm is radius, it's half the diameter. It's perpendicular to my chord, therefore it's bisecting that chord. So Sn is congruent to Sp. And I've created this right triangle in which I know this leg of my right triangle is 8. And I know that I want to find this leg of my right triangle. And I know the hypotenuse is 17. So anytime I have 2 out of my 3 legs of my right triangle, I'm going to use Pythagorean theorem to set it up and solve for the missing leg. So I say 17 squared, which is 289, is equal to 64 plus x squared. I'm going to subtract my 64 over. That's going to give me a total of 225 is equal to x squared. And now I need to take the square root of both sides, and x is going to give me 15. So the value of x here is 15, which if I look back at my picture is half of my chord. So my full length of my chord, NP, has got to be equal